Hi, you guys. Happy Thursday. Hopefully, you have completed the mole and molar mass POGL. So now you're ready to start talking about molar mass and mole volume relationships. So that's what I'm going to go over in this lecture today. I would recommend that you write some of this stuff down, take some notes, write down some examples so that you have references to look at while you are working on some of your worksheets over the next couple of days while I'm still out of town. So molar mass is the mass in grams on 1 mole of the compound. So if you have 1 mole of a substance, the mass of that mole is the molar mass. So we could look at something like glucose, for example, which is a really important molecule in the world of biology. And we could calculate its molar mass by simply adding up the mass of each of the elements involved. So we have 6 carbons with a mass of 12.01 grams per mole each, right? Since it's molar mass, it would be 12.01 grams plus 12 hydrogens. Their mass is 1.01. Plus 6 oxygens, which is about 16. If you don't want to use all the decimals, that's okay. Your number will be a little bit different, but not noticeably different. So 6 times 12.01 plus 12 times 1.01 plus 6 times 16 equals 180.18 grams. And so we're saying really just grams because we already know that it's in 1 mole because we're saying that it's the molar mass. So you simply add up the weighted average atomic mass for each element from the periodic table multiplied by the number of times it occurs in the compound to get your molar mass. So every compound has a really distinct molar mass. Oh, well, there you go. That's what I just did, but more complicated. So here's a couple examples of calculating molar mass. I would recommend that you go ahead and pause the video right now and just try to calculate these on your own and see if you can come up with the right answer. Did you pause the video? Okay, so I'm going to go through these really quick. We'll start with water. So for H2O, we would have 2 hydrogens plus the 1 oxygen. And so the molar mass of water is about 18.02. And you'll see me write the symbol for molar mass as kind of this cursive capital M. That's just convention. There's so many M's in chemistry, right? We've got moles, we've got mass, we've got molar mass, and so we really want to be able to tell them apart. And so that's why we use the molar mass as a capital cursive M. Carbon dioxide, we have 1 carbon plus 2 oxygens, and so that's going to give us about 44 as the molar mass. When you do a lot of chemistry like I do, you start memorizing molar masses and then you're like, wow, this is cool. Last one is phosphoric acid. So that's 3 hydrogens plus a phosphorus, which is about 31, plus 4 oxygens, which is about 16. And if you're worried about the rounding, you can kind of show it to yourself with the rounding and without the rounding and kind of see what the difference is. So here we have 98 grams is the molar mass of phosphoric acid. If I calculate it with all the decimals, I wind up with 4 times 15.999, the exact same answer. So in this case, it really doesn't make a difference at all. All right. So molar mass is actually super practical for us because, we talked about we use moles because there's such large numbers of atoms and such large number of molecules in the samples of stuff that we deal with. And so molar mass really comes in handy because it's like a bridge between the mass that we can measure and the quantity of molecules, the moles, that we're wondering about. And so moles are really powerful, and we'll start to see that in our next unit. And so it's really neat that molar mass just elegantly lets us switch back and forth between moles and mass. So if we wanted to look at how many moles were in C2H6, when we have 105.28 grams of that chemical, we can use our molar mass as a conversion factor. So I can calculate my molar mass and say, okay, 2 carbons plus 6 hydrogens is going to be about 30, I think. Sometimes I can do math. Yeah, it's going to be about 30. So 30 grams per 1 mole. So that's our conversion factor. And it's asking me about 105.28 grams of C2H6. So I'm going to start with my 105.28 grams of C2H6 and make my cancellation line. I'm going to say, okay, my 30 grams should go on the bottom so that it cancels out. And my 1 mole will go on top. Okay, so grams cancel. And now I have 105.28 divided by 30 times 1. So I have 3.51 moles of C2H6 in this sample. As we get farther into using cancellation lines and using moles and converting from mass, the cancellation line formatting is going to become more important, even though intuitively right now a lot of us could do the math for this and figure this out much more simply than using a cancellation line, but I'm really trying to lay the foundation for something farther down the road. So go ahead and use the cancellation line, and if you don't like it, too bad. Okay, so go ahead and pause it right now. Try this next calculation on your own. See if you can go the other way. What is the mass of 1.68 moles of iron chloride? So there's 1.68 moles as your starting point. Iron 3 chloride is your compound. So go ahead and pause it and see if you can go back the other way. The molar mass of iron 3 chloride is going to be 55.85 plus 3 times 35.453. So we get 162.21 grams in 1 mole. And now I'm ready to figure out the mass. So I'll start with my 1.68 mole of, get out of here, iron 3 chloride. And then I have that 1 mole of iron 3 chloride is equal to 162.21 grams of iron 3 chloride. So then I can just multiply together and I wind up with 272.51 grams of iron 3 chloride. Okay. So you can begin to see that you can go back and forth from mass to moles and from moles to mass pretty easily using molar mass. All right, here is some more practice for you. Please pause the video and go through and practice these so that you feel pretty confident about them. All right, hopefully you've had time to work these out after you stopped the video. So for the first one, we have 2.7 moles of sodium sulfate. Oh, I forgot the A. And we have 184.1 grams of magnesium bromide. Additionally, we can investigate relationships between moles and the volume that the moles of a gas are occupying. So at standard temperature and pressure, STP, which is defined as 0 degrees Celsius and 1 atmosphere, 1 mole of gas is occupying a volume of 22.4 liters. We call this molar volume. That means that 1 mole of gas has 22.4 liters of gas. So this is just another conversion factor for us. If we want to use this conversion factor, it's very straightforward. We have 84.0 liters of CO2. Conversion factor 22.4 liters of CO2 is 1 mole of CO2. 84.0 divided by 22.4 gives us 3.75 liters of carbon dioxide. We can also go the other way. So if we start with 0.125 moles of N2 nitrogen gas, and then we have 1 mole of nitrogen is equal to 22.4 liters of nitrogen. We can simply multiply across the top to get our volume of our gas. So it would be occupying 2.8 liters of nitrogen gas. Very straightforward. I think the really important thing to remember here is that unlike with molar mass, where your conversion factor changes depending on the compound, when you're dealing with the mole volume relationship, the conversion factor always stays the same. It's always this 22.4 no matter what gas you're talking about. If it's at standard temperature and pressure, it's always 22.4. All right, we are almost done. Here's a little practice for you. Go ahead and run through these two on your own. Pause the video and then check your answers. All right, I threw you guys a couple of curveballs on this one. You need to use the mole volume and then go back and use some conversion factors that we've used in the past. So for the first one, 39.2 liters of oxygen, 22.4 liters of oxygen in 1 mole of oxygen, and in 1 mole of oxygen there's 6.02 times 10 to the 23rd molecules. So you end up with 1.05 times 10 to the 24 molecules of O2. All right, so I don't have time to go through the second problem because of this recording, but the answer is 160 grams.